Welcome to this explainer of the source material. Today, we're diving into what I like to call a high-stakes mathematical detective story. We're going to look at the fabric of the universe itself, but not through the lens of messy physical matter. No, we're looking through the pure, crystalline elegance of structural geometry. We are on the hunt for a single elusive number, the ground eigenvalue. This is essentially the lowest natural resonant frequency of the universe's geometric boundary. And we're going to watch as two entirely independent mathematical proofs converge to trap it.
Now, it sounds kind of like magic, right? I mean, how does pure geometry dictate the vacuum of the universe? Well, our sources today propose something absolutely breathtaking. They suggest that the vacuum energy of the cosmos, what physicists usually call dark energy, isn't some mysterious invisible substance at all. Instead, it's just the lowest resonant frequency of the universe's fundamental shape. To really grasp this, we have to look at the topology of a non-orientable surface. So let's set the stage.
Section 1. The curved Mobius band.
To get this investigation started, we need to set up our topographical scene. We're working on a very specific stage today, the Mobius band. But not just any Mobius band. We're looking at the minimal, non-orientable surface with a single closed boundary loop or an S1 boundary. Think of that classic visual of the Mobius twist. Because of this twist, the surface literally has no distinct inside or outside. If a mathematical field travels all the way around this loop, it doesn't just arrive back where it started. The geometry physically forces the field to flip its sign. It's called an anti-periodic boundary condition. It's this incredibly elegant twist built right into the shape itself.
And notice the specific curvature we're dealing with here. This isn't a flat, twisted ribbon sitting on your desk. This Mobius band is constructed from a spherical band on a great S2 sphere, which is itself embedded in an S3 hypersphere. Because of this, it inherits a totally geodesic constant curvature metric. The math gives us a constant Gaussian curvature, k, equal to 1 over r squared. This takes abstract topology and turns it into rigorous physical geometry that we can actually measure.
Section 2, the direct computation.
Okay, with our stage set, we can start the first of our two independent mathematical ascents up the mountain. Our goal? To find the absolute lowest frequency that this curved surface can support. Think of these computational steps as elegant natural laws just unfolding. First, we establish our ground eigenfunction. On a flat strip, both sine and cosine work, but the curvature of our space uniquely selects sine. So our eigenfunction is sine of y over r. Next up, we apply the twisted Laplace-Beltrami operator. This is basically the geometric equivalent of plucking a guitar string to see how it vibrates. Finally, we compute the explicit Rayleigh quotient, which tests this function against the energy of the surface.
When you actually run the calculus, something absolutely beautiful happens. The explicit computation yields a firm mathematical upper bound. It establishes an absolute ceiling for our elusive frequency, proving that the ground eigenvalue, lambda 0, must be less than or equal to 2 over r squared.
2 over r squared? I really want you to lock this number in your mind. We've hit our ceiling. But, in mathematics, an upper bound is really only half the story. To know exactly what the number is, we have to prove it can't go any lower either.
Section 3. The Bochner lower bound.
This brings us to our second, entirely independent proof. We're shifting gears to take the scenic route, so to speak, a topological method that's going to establish a structural floor for our eigenvalue. To do this, we use something called the Bochner identity. It's a hugely powerful tool for finding lower bounds, but there is a major hazard on this path. Because of how the Mobius quotient is constructed, the transverse width of our band metrically collapses to a single point in the center, specifically at y equals pi times r over 2. This creates a genuine cone point with an angular deficit. It is a mathematical singularity, basically a black hole in our equation that threatens to break the entire proof.
Section 4. Cone point excision.
To survive this metric degeneration, mathematicians use an incredibly ingenious trick, a topological secret weapon known as cone point excision. We mathematically cut a tiny circle around the dangerous singularity. And because the eigenfunction is on the regular branch, which just means it flattens out as it approaches the maximum at the cone point, the boundary terms of our excision completely vanish as that circle shrinks to 0. Just like that, the singularity's threat is entirely neutralized.
So what's really interesting here is how perfectly these elements just lock together. The outer boundary curves of our surface are totally geodesic, meaning there's zero edge flux escaping.
And as we just saw, the excision boundary terms completely vanish at the singularity. With all those hazards neutralized, we can finally apply a trace inequality to the Hessian of our function.
And the result? A totally triumphant structural floor. The Bachner formula proves that our eigenvalue, lambda, must be greater than or equal to 2 over r squared. That floor absolutely cannot be breached.
Section 5. The perfect match. All right, we have now completed both independent mathematical ascents. It's time for the climax of our explainer, where these two paths finally converge. Just think about this incredible pincer movement. Through direct computation, we established the Rayleigh upper bound. Our eigenvalue is less than or equal to 2 over r squared. Then, through the Bachner identity and cone point excision, we established the lower bound. Our eigenvalue is greater than or equal to 2 over r squared. The ceiling and the floor squeeze together perfectly, completely trapping our exact ground eigenvalue right between them.
And there it is again, 2 over r squared. It is honestly awe-inspiring to see two totally distinct proofs, one relying on a test function, the other relying purely on geometric identities, walk into the exact same truth. But you might be wondering, why this specific number? Well, 2 over r squared is definitely not a coincidence. It's the exact intrinsic scalar curvature of this embedded surface. This is the profound revelation here. The lowest resonant frequency of this topological space is absolutely identical to the physical curvature of the space itself. To put that into perspective, if we did this exact same math on a flat Mobius strip, the lowest eigenvalue would just be 1 over r squared. But our surface isn't flat. It inherits constant positive curvature from its covering sphere. That curvature itself acts upon the equations, naturally supplying the magic missing factor of 2. The geometry itself lifts the flat model into the actual physical reality of our universe. And this brilliantly illustrates why all of this complex math actually matters to our understanding of the universe. I mean, how does a 2D surface frequency map to the 3D space we actually live in? We get there through something called the Gauss equation interface. Our topological eigenvalue of 2 over r squared is multiplied by a conversion factor of 3 over 2 from the Gauss equation. The net product of that is exactly 3 over r squared. And get this, in the framework of standard cosmology, 3 over r squared is the precise value of the cosmological constant, lambda. This is a literal paradigm shift. This derivation proves that the cosmological constant, the force driving the expansion of the universe, is not some mysterious, untestable dark energy. Actually, scratch that. It's simpler than that. It is simply the ground mode eigenvalue of the cosmic boundary. It's the natural geometric resonant pattern of the universe's topology. Back in 1917, Einstein introduced the cosmological constant and later called it his biggest blunder. But as this derivation shows, he was right all along. For topological reasons no one at the time could have possibly known, which leaves us with a truly staggering thought to wrap up our explainer today. If the physical vacuum of the universe, the very foundation of our reality, is nothing more than the lowest mathematical frequency of a curved Mobius band, what other massive cosmic mysteries are just sitting there, waiting for the right topological proof to unlock them? Keep wondering, keep looking at the structure of things, and I'll catch you next time.